Hello, in this lecture we'll answer two questions. In the first question, we'll find out the length of tangent MF that is equals to x. And in the second question, we'll find out the length of this tangent AP that is also equals to x. So we'll start with the first question. In the drawing, we have three identical circles, and we also have the big tangent ABC. The big tangent ABC is tangent to this circle at point A, it is tangent to this middle circle at point B, and it is tangent to this circle at point C. In addition, we have this common start point M. From this common start point M, we have tangent MD that is tangent to this circle at point D, and the length of tangent MD is 5 units. In addition, we have also tangent ME that is tangent to this middle circle at point D here, and the length of tangent ME is 7 units. And finally, we have also tangent MF that is tangent to this circle at point F, and the length of tangent MF is x. And our mission is to find out the length of this tangent MF that is equal to x, so we have to find out the value of x. In addition, we know that side AB equals to side BC equals to 3 units in its length. Okay, so first of all, we define the center of this circle, this point as point P. We define the center of this middle circle, this point is point Q. And finally, we define the center of this circle, this point is point S. In the next step, we join points P and D together by a straight line. PD is of course the radius of this circle. We define the radius of this circle as R. Because of the fact that those three circles are identical circles, the radius of those circles must be equal to each other. Okay. Also, the radius of those two circles will be also equal to R. And here we have the radius PD that is equals to R. The radius PD is drawn to point D, that is the point of tendency of tangent MD with this circle. And whenever you have a radius that is drawn to the point of tendency, then according to one, tangent MD will be perpendicular to the radius of DP. If MD is perpendicular to DP, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points M and P together by straight line. When joining points M and P, we create the right triangle MPD. So, in the next step, we implement the Pythagoras theorem on this right triangle MPD. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle MPD is MP. Therefore, the square of the hypotenuse is MP square, and it is equals to PD square plus MD square. So, I'll write it down. MP square, that is the square of the hypotenuse, is equal to PD square plus MD square. Okay, again, according to equation 1, we actually found out that MP square equals to PD square plus MD square. MP is the missing tangent, so we write as it is. So it is MP square that is equal to PD square. PD is R, therefore PD square is R square plus MD square. MD is 5, therefore MD square is 5 square, that is 25. So in total, according to equation 1, we have found out that MP square equals to R square plus 25. We repeat on the same process on this middle circle. That is to say, we join points Q and E together by straight line. QE is of course the radius of this circle that is equals to R. According to the same rule, because of the fact that the radius QE is known to point E, that is the point of tendency of the let ME with this middle circle, and whenever you have a radius that is known to the point of tendency, then tangent ME will be perpendicular to the radius EQ. If ME is perpendicular to EQ, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points M and Q together by straight line. By joining points M and Q, we get the right triangle MQE. So we implement the Pythagoras theorem on this right triangle MQE. According to the Pythagoras theorem on this right triangle MQE, MQ squared, that is the square of the hypotenuse, equals to QE square plus EM square. And again, according to the Pythagoras theorem, in this right triangle MQE, MQ square equals to QE square plus EM square. MQ is the missing tangent, so we leave it as it is, so it is MQ square equals to QE square. QE is R, therefore QE square is R square plus ME square. ME is 7, therefore ME square is 7 square, that is 49. So in total, according to equation 2, we actually found out that MQ square equals to R square plus 49. We repeat on the same process in this right circle. That is to say, we join points S and F together by straight line. SF is of course the radius of this circle, that is equals to R, and according to rule 1, because of the fact that the radius SF is on to point F, that is the point of tendency of tangent MF with this circle, whenever you have a radius that is on to the point of tendency, then tangent MF will be perpendicular to the radius FS. If MF is perpendicular to FS, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points S and M together by straight line. By joining points S and M, create the right triangle MSF. So we implement the Pythagoras theorem on this right triangle MSF. According to the Pythagoras theorem on the right triangle MSF, MS squared, that is the square of the hypotenuse, is equal to SF square plus MF square. And again, in the right triangle MFS, according to the Pythagoras theorem, ms squared, that is the square of the hypotenuse, equals to sf squared plus mf squared. ms is the missing tangent, so we leave it as it is, so it is ms squared equals to sf squared. sf is r, therefore sf squared is r squared plus mf squared. mf is x, therefore mf squared is x squared. X is the tangent that we are looking for in this question. So according to equation 3, we should found out that ms squared equals to r squared plus x squared. In the next step, we will join points P and A together by straight lines. PA is the radius of this circle that is equal to R. And again, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. The next time we join points Q and B together by straight line. QB is the radius of this circle is equals to R, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And finally, we join points S and C together by a straight line. SC is also the radius of this circle that is equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, we know that the distance of those 3 points P, Q, and S from the straight line ABC is equal to R. They have the same distance. They are the same distance from the straight line ABC. Therefore, the 3 points P, Q, and S must be located on one straight line. That is to say, PQS is one straight line. And exactly because of the same reason that the 3 points P, Q, and S are at the same distance from the straight line ABC, therefore the straight line PQS is parallel to the straight line ABC. And because of the fact that PQS is parallel to ABC, you can implement here rule 17. So let me click on rule 17. According to rule 17, the sum of one-sided interangles that are located between the parallel lines is equal to 180 degrees. So in the moment we have line A that is parallel to line B. The red line is line C that intersects with those two parallel lines A and B at those 2 points. In addition, we have those 2 angles, alpha and beta. Because of the fact that those 2 angles, alpha and beta, they are located on the same side of the straight line C, that is to say they are located on the right side of the straight line C, they are defined as one-sided angles. And because of the fact that those 2 angles, alpha and beta, they are located between the parallels A and B, they are also defined as interior angles. So in total, those 2 angles, alpha and beta, they are defined as one-sided interior angles. And according to this rule 17, the sum of two one-sided interrogals is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we can implement rule 17 in our drawing. In our drawing, we have those two angles. Those two angles are defined as one-sided interangles. And according to rule 17, the sum of two one-sided interangles is equal to 180 degrees. So the sum of those two angles must be equal to 180 degrees according to rule 17. This is a right angle, that is to say it is equal to 90 degrees in its size. So 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore this missing angle must be equal to 90 degrees in its size. Likewise, those two angles are also defined as one-sided interangles. According to rule 17, the sum of those two angles is equal to 180 degrees. This angle equals to 90 degrees plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. Those two angles are also defined as one-sided interangles. This angle is equals to 90 degrees plus this missing angle. In total must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its side. And finally, those two angles are also defined as one-sided interangles. This is a right angle, that is to say it is equal to 90 degrees in size. So this right angle plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees in its size. So inside this quadrilateral PQBA, we have four right angles, and according to rule 5, any quadrilateral that has four right angles must be this rectangle if not a square. So in relation to this quadrilateral PQBA, it's a rectangle because it has four right angles. So already know this is quadrilateral PQBA, and it is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PQBA, side PQ must be equal to the opposite side AB. But AB is 3, therefore the opposite side PQ must be also equal to 3 units in its length. Likewise, inside this quadrilateral QSCB, we have four right angles. Therefore, according to rule 5, this quadrilateral QSCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle QSCB, side BC must be equal to the opposite side QS. But BC is 3, therefore QS must be also equal to 3 units in its length. In the next step, I'll copy the big triangle MPS in a new page, and we now have this big triangle MPS. So actually, this is the big triangle MPS that I covered from the original drawing. This point Q. The red line is line 7th MQ. Line 7th MQ is the median of this triangle MPS. The definition of a median is a line segment that connects the vertex of the triangle to the midpoint of the opposite side. In this triangle MPS, the median MQ connects the vertex M at the midpoint of side PS. The midpoint of side PS is Q. Why the midpoint of side PS is Q? Because PS in total equals to 3 plus 3, that is 6. And at point Q, side PS has been bisected into two halves. Each half equals to 3 units. PQ equals to 3 units, and QS equals to 3 units in its length. So the median MQ bisects the opposite side PS. Again, the median of a triangle connects the vertex M to the midpoint of side PS. The midpoint of side PS is Q. That is to say, the median MQ bisects chord PS. So the median of any triangle bisects the opposite side to the vertex. Here the median MQ exits from the vertex M and it bisects the opposite side PS. That is to say, it divides side PS into two halves. Each half equals to 3 units in its length. But the question is, what is the length of the median MQ? Actually, we have a special formula that will help us to find out the length of MQ, the median MQ. So, this is triangle ABC. The length of side AB is B units, the length of this side AC is C units, and the length of this side BC is A units. And line 7 AD, the red line 7 AD is the median of this triangle ABC. The median AD exits from the vertex A and bisects the opposite side BC. That is to say, the median AD divides side BC into two halves. The first half is BD and the second half is DC. So the median of any triangle bisects the opposite side to the vertex into two halves. The opposite side of vertex A is BC, so the median AD bisects side BC into two halves. The first half is BD and the second half is DC. But what is the length of the median AD? The length of the median AD is equal to 2b squared plus 2c squared minus a squared divided by 2. Repeat again, the length of the median AD is equal to the square root of 2b squared plus 2c squared minus a squared over 2. We'll use this special formula in order to find out the length of the median MQ of this triangle MPS. According to the special formula, the length of the median MQ will be equal to the square root of 2 times MP squared plus 2 times MS squared minus PS squared divided by 2. Repeat again, the length of the median MQ is equal to the square root of 2 times mp squared plus 2 times ms squared minus ps squared divided by 2. Here we will multiply this equation 1 by 2, and we get that two times mq is equal to the square root of 2 times mp squared plus 2 times ms squared minus ps squared. Repeat again. After we multiply this equation 1 by 2, we actually found out that two times mq equals to the square root of 2 times mp squared plus 2 times ms squared minus ps squared. Here we'll square both sides of this equation 1. And we get that 2mq squared is 2 squared, that is 4, times mq squared. We'll square this side of equation 1. And because of the fact that the square and the root are two opposite operations, the square will cancel the root, and we left only with what is inside this root. That is to say, we left only with 2 times mp squared plus 2 times ms squared minus ps squared. So according to equation 1, 4 times mq squared, according to this equation 2, mq squared equals to r squared plus 49. Therefore, we substitute mq squared here by r squared plus 49, and it is equal to 2 times mp squared. According to equation 1, mp squared equals to r squared plus 25. Therefore, we substitute mp squared here by r squared plus 25. And we have also here 2 times ms squared. According to equation 3, ms squared equals to r squared plus x squared. Therefore, we substitute ms squared here by r squared plus x squared, and we have also here minus ps squared. From the drawing, it is very easy to see that ps in total equals to 3 plus 3, that is 6. If ps equals to 6, it means that ps squared must be equal to 6 squared, that is 36. So minus ps squared is minus 36. We'll open the brackets on both sides of this equation 1, and we get that 4 times r squared plus 4 times 49 is 196 equals to 2 times r squared. 2 times 25 is 50, so it is plus 50. And we have also 2 times r squared plus 2 times x squared minus 36. In this side of the equation 1, we have 4r squared. On the other side of this equation 1, we have 2r squared plus 2r squared, that is 4r squared. So 4r squared will get cancelled. We have 4r squared, and 2r squared plus 2r squared is also 4r squared, that will be cancelled. After we cancel 4r squared, in this side of equation 1, we left only with 196. On the other side of this equation 1, we have 50 minus 36 is 14. And we also here plus 2x squared. So in total, according to equation 1, 196 equals to 14 plus 2x squared. Here we subtract 14 from this equation 1. Finally get that 196 minus 14 is 182, and 182 equals to 2x squared. Here we divide this equation 1 by 2, and we get that 182 over 2 is 91, so 91 equals to x squared. Here we take a root out of this equation, and finally we get that x is the variable that we're looking for. X equals to either the square root of 91. The square root of 91 is 9.54 units. And that is the answer to the question. Repeat again, we have found out that the length of this standard MF is equals to x is equal to either the square root of 91 units, or in terms of numbers, the length of this standard MF is equals to x is equal to 9.54 units. So we finished with the first question. And the next time I present to you the second question, and solve the second question of this lecture. Our mission in the second question is to find out the length of this standard AP is equals to x. We have to find out the value of x. So in the drawing, we have quarter circle AOB. This is quarter circle AOB. Inside this quarter circle AOB, we have this small circle. Line segment OB is tended to this small circle at point Q. We also know that line segment OQ equals to 5 units in this line. In addition, we know that the circle, the small circle and the big quarter circle touch each other internally in this point. So we define the touching point, this point as point K. Tangent AP is tangent to this small circle at point P. Tangent AB equals to x units in itself, and our mission is to find out the value of x. It is the length of tangent AP. In the first step, we define the center of this small circle. This point is point C. And we join point C and Q together by a straight line. CQ is of course the radius of this small circle. We define the radius of this small circle as A. CQ equals to A. Here actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we join points C and P together by a straight line. CP is of course the radius of this small circle that is equal to A, and according to the same rule 1, this angle equals to 90 degrees. In the next step, we join points A and C together by a straight line. By joining points A and C, we create the right triangle APC. So in the next step, I'll copy the right triangle APC in a new page, and we'll implement the Pythagoras theorem on this right triangle APC. Here by PT is the abbreviation for Pythagoras theorem. So really this is the right triangle APC that according to the original drawing. This right triangle APC according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AP squared plus PC squared. So I write it down. This will be equation 1. AC squared, that is the square of the hypotenuse, equals to AP squared plus PC squared. AC is the missing tangent, is the missing hypotenuse, so the limit is it, so it is AC squared equals to AP squared. AP is x, therefore AP squared is x squared plus PC squared. PC is a, therefore PC squared is a squared. So in total, according to equation 1, we actually found out that AC squared equals to x squared plus a squared. So we have, as I already mentioned before, point K is the touching point between the big quarter circle and this small circle. That is to say, they touch each other internally at point K. Remember, we have internal notch between two circles, or semicircles, or quarter circles. You can implement rule 9. So I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects the centers together passes through their touching point. So in the moment we have two circles. The center of this big circle is 0 at point O. The center of this small circle is 0 at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is point P. Again, according to this rule 9, the straight line OM must pass through for point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. So we can actually implement rule 9 in our drawing. Why? Because in our drawing we have an internal notch between the small circle and the big quarter circle. That is to say they touch each other internally at point K. Therefore we can implement rule 9. The center of this big quarter circle is 0 at point O. The center of this small circle is 0 at point C. And the straight line that connects the centers together is the straight line OC. And according to rule 9, this straight line OC must pass through their touching point, that is point K. Again, according to rule 9, the straight line OC must pass through point K, that is their touching point. Or OCK is one straight line. Again, OCK is one straight line according to rule 9. So we join points O and C together by straight line, and according to rule 9, the straight line OC must pass through point K, that is their touching point. It's very easy to say from the drawing that the straight line OC that passes from point K, that is the touching point. What is the definition of CK? CK is of course the radius of this small circle, that is equals to A. What is the definition of line segment OK? OK is of course the radius of this quarter circle. So we define the radius of this quarter circle as B. Therefore OK equals to B. It is the radius of the quarter circle. We also know that OB equals to B. It is also the radius of the quarter circle. OA is also equals to B. It is also the radius of this quarter circle. What is the length of the missing line 7, line 7 OC? For the moment, it is very easy to see that OC in total equals to OK minus CK. Again, OK minus CK equals to OC. So I write it down. OC equals to OK minus CK. That is to say, OC in total equals to OK. OK equals to B. It is the radius of the quarter circle. That is equals to B. Minus CK. CK is A. It is the radius of the small circle, that is A. So in total, OC equals to B minus A units in its length. In the next step, we'll copy the right triangle OCQ in a new page, and we will implement the Pythagoras theorem on this right triangle OCQ. Here by PT is the version for Pythagoras theorem. The hypotenuse OC of this right triangle OCQ is B minus A. Side CQ equals to A units in its length. It is the radius of the small circle. And finally, side OQ equals to 5 units in its length, according to what is given as the question. So actually, this is the right triangle OCQ that I covered from the original drawing. According to the Pythagoras theorem, this right triangle OCQ, OC squared, that is the square of the hypotenuse, equals to CQ squared plus QO squared. So I write it down. This will be equation 2. OC squared, that is the square of the hypotenuse, is equal to CQ squared plus OQ squared. OC is B minus A, therefore OC squared is B minus A squared, and it is equal to CQ squared. CQ is A, therefore CQ squared is A squared plus OQ squared. OQ is 5, therefore OQ squared is 5 squared, that is 25. So in total, according to equation 2, we shall find out that B minus A squared equals to A squared plus 25. B minus A squared is B squared plus A squared minus 2 times A times B, and it is equals to A squared plus 25. So here we have A squared on both sides of this equation 2, so A squared will get cancelled. After we cancel A squared, in this side of equation 2, we left only with B squared minus 2AB. On the other side of this equation 2, we left only with 25. So in total, according to equation 2, we actually found out that B squared minus 2AB equals to 25. in the next step, we will do a construction. That is to say, from this point C, that is the center of this small circle, from point C, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AO. This point is point N. By doing this construction, we get quadrilateral NCQO. This is quadrilateral NCQO. Inside this quadrilateral NCQO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-facing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4-facing angle must be equal to 90 degrees in its size. So actually, inside this quadrilateral NCQO we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral NCQO as a rectangle because it has 4 right angles. So write it down. This is quadrilateral NCQO, that is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NCQO, side NC must be equal to the opposite side OQ. But OQ is 5, therefore NC must be also equal to 5 units in its length. So NC equals to 5 units. Likewise, according to the same rule, in the same rectangle NCQO, side CQ must be equal to the opposite side NO. But CQ is 8, is the radius of the small circle that is 8. CQ is 8, therefore the opposite side NO must be also equal to 8 units in its length. What is the length of the missing 97 AN? From the drawing, it is very easy to see that AN equals to AO minus NO. Again, AN in total equals to AO minus NO. So I'll write it down. AN equals to AO minus NO. So AN in total equals to AO. AO is the radius of the big quarter circle that is B. Minus NO. We just write down found out that NO equals to A. So in total, AN equals to B minus A units in its length. AN equals to B minus A units in its length. In the next step, I'll copy the right triangle A and C in the new page and we will implement the Pythagoras theorem on this right triangle A and C. Here by PT is the abbreviation for Pythagoras theorem. We just right now found out that side AN equals to B minus A. Side NC equals to 5 units in its length. And AC is the missing side. So this is the triangle A and C that are covered from the original domain. In this triangle A and C, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AN squared plus NC squared. So I'll write it down. This will be equation 3. AC squared, that is the square of the hypotenuse, is equal to AN squared plus NC squared. AC is the missing side, but according to equation 1, according to this equation 1, AC squared equals to X squared plus A squared. Therefore, we substitute AC squared in this equation 3 by X squared plus A squared. And it is equal to AN squared. AN is B minus A, therefore AN squared is B minus A squared plus NC squared. NC is 5, therefore NC squared is 5 squared, that is 25. So in total, according to equation 3, we should find out that X squared plus A squared equals to B minus A squared plus 25. So according to equation 3, I should find out that X squared plus A square equals to B minus A square. B minus A square equals to B square plus A square minus 2 times A times B plus 25. So here we have A square on both sides of this equation 3, so A square will get cancelled. After you cancel A square, in this side of equation 3 we left only with X square, and the other side of equation 3 we left with B square minus 2 times AB plus 25. Repeat again, according to equation 3, I shall find out that X square equals to B square minus 2 times AB plus 25. But according to this equation 2, B square minus 2AB equals to 25. Therefore, we substitute B square minus 2AB here in this equation 3 by 25. And we get that according to equation 3, X square equals to, again, B square minus 2AB according to this equation 2 is 25. And we also here 25. So in total we found out that X square equals to 25 plus 25, that is 50. So X square equals to 50. Here we take a root out of this equation, and finally we get that X equals to the square root of 50. So X equals to the square root of 50. 50 is 2 times 25, and the square root of 25 is 5. So in total this expression equals to 5 times square root of 2. 5 times square root of 2 is equal to 7.071 units. That is the answer to the question. Repeat again, we should find out that the length of this line segment, the length of this line segment AP is equals to X. It is equal to either 5 times square root of 2 units. In terms of numbers, AP is equals to X is equal to 7.071 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission, this first question, is to find out the length of this tangent MF is equals to X. We have to find out the value of X. So in the domain we have three identical circles, and we also have the big tangent ABC. Tangent ABC is tangent to this circle here at point A it is tangent to this middle circle here at point B, and it is tangent to this circle here at point C. In addition, we have, this is the common extent point M. From this common extent point M, we have tangent MD that is tangent to this circle at point D. The length of tangent MD is 5 units. In addition, we have also from the same common extent point M, tangent ME that is tangent to this middle circle at point T, and the length of this tangent ME is 7 units. And finally, we also have tangent MF that is tangent to this circle at point F, and the length of tangent MF is x. And our mission is to find out what is the length of tangent MF that is equal to x. So what is the value of x? So first of all, we define the center of this circle here. This point is point P. We define the center of this middle circle. This point is point Q. And finally, we define the center of this circle. This point is point S. In the next step, we join points P and D together by straight line. PD is the radius of this circle. We define the radius of this circle as R. And because of the fact that those three circles are identical, it means that the radii of the other two circles must be also equal to R. So we join points P and D together by straight line. According to rule 1, this angle equals to 90 degrees. In the next step, we copy the right angle MPD in the new page and represent the Pythagoras theorem on this right angle MPD. According to the Pythagoras theorem, in this right angle MPD, MP squared, that is the square of the hypotenuse, equals to PD squared plus MD squared. So MPD again, according to the Pythagoras theorem, in the right angle MPD, MP squared equals to PD squared plus MD squared. MP is the missing side, so we leave it as it is. So it is MP squared equals to PD squared. PD is R, therefore PD squared is R squared plus MD squared. MD is 5, therefore MD squared is 5 squared, that is 25. So in total, according to question 1, we should find out that MP squared equals to R squared plus 25. We repeat it on the same process on this middle circle. That is to say, we join points Q and E together by straight line. Q is the radius of this circle, that is R. According to 1, this angle equals to 90 degrees. We join points M and Q together by straight line. By joining points M and Q, we get the right triangle MQE. In the next step, we implemented the Pythagoras theorem on this right triangle MQE. According to the Pythagoras theorem, in this right triangle MQE, MQ squared, that is the square of the hypotenuse, equals to QE squared plus EM squared. Repeat again, according to the Pythagoras theorem, in the middle right triangle MQE, MQ squared equals to QE squared plus EM squared. MQ is the missing hypotenuse, so we leave it as it is. So it is MQ squared equals to QE squared. QE is R, therefore QE squared is R squared plus ME squared. ME is 7, therefore ME squared is 7 squared, that is 49. So in total, according to equation 2, I shall find out that MQ squared equals to R squared plus 49. We repeat it on the same process on this circle. That is to say, we join points S and F together by straight line. SF is the radius of this circle, that is R. According to rule 1, this angle equals to 90 degrees. In the next step, we join points M and S together by straight line. By joining points M and S, we get the right big triangle MSF. In the next step, we implemented the Pythagoras theorem on this right big triangle MSF. According to the Pythagoras theorem on this right triangle MSF, MS squared, that is the square of the hypotenuse, equals to SF squared plus FM squared. Again, according to the Pythagoras theorem, in the right triangle MSF, MS squared equals to SF squared plus MF squared. SF is R, therefore SF squared is R squared. FM is X, therefore FM squared is X squared. So in total, according to the Pythagoras theorem, in the right triangle MSF, SM squared equals to R squared plus X squared. In the next step, we join points P and A together by straight line. PA equals to 90. PA is the radius of this circle, that is equal to R, according to our definition. And this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we join points Q and B together by straight line. QB is also the radius of this circle, that is R, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Finally, we join points S and C together by straight line. SC is also the radius of this circle, that is R, And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Those 3 points, P, Q, and S, they're all in the same distance from the straight line ABC, and therefore those 3 points, P, Q, and S, must be located on one straight line. That is to say, PQS is one straight line, and because of the same reason that the 3 points P, Q, and S are at the same distance from the straight line ABC, therefore the straight line PQS must be parallel to the straight line ABC. So, and therefore we can implement here rule 17. So I'm just clicking on rule 17. According to rule 17, the sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. So in the moment we have line A that is parallel to line B, the line C intersects with those two lines A and B at those 2 points. In addition, we have those 2 angles alpha and beta that are defined as one-sided interior angles, and according to this rule 17, the sum of 2 one-sided interior angles is equal to 180 degrees. That is to say, alpha plus beta equals to 180 degrees. We can implement rule 17 in our drawing. Why? Because in our drawing, those two angles are defined as one-sided interior angles. And because of the fact that those 2 angles are located between the parallel lines PQS and ABC, the sum of those 2 angles must be equal to 180 degrees according to rule 17. This is the right angle. That is to say, it is equal to 90 degrees in size. So 90 degrees plus this missing angle, in total the sum of those 2 angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in size. According to the same rule, because of the fact that those 2 angles are defined as one-sided interior angles and are located between the parallel lines PQS and ABC, the sum of those 2 angles must be equal to 180 degrees according to rule 17. But this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees in size. Likewise, those 2 angles are also defined as one-sided interior angles. This angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees in its size according to rule 17. And finally, those 2 angles are also defined as one-sided interior angles, and the sum of those 2 angles is equal to 180 degrees. But this is a right angle. Therefore, this missing angle must be also equal to 90 degrees in size according to rule 17. So in total, inside this quadrilateral PQBA, we have 4 right angles. Therefore, according to rule 5, this quadrilateral is a left angle, but we also know that the opposite sides of left angle are equal to each other. So left angle PQBA, side AB must be equal to the opposite side PQ. But AB is free according to what is given as the equation, therefore the opposite side PQ must be also equal to 3 units in its length. Likewise, inside this quadrilateral QBCS, we have 4 right angles, and therefore according to rule 5, it is a left angle. But we also know that the opposite sides of left angle are equal to each other. So left angle QS BC, side BC must be equal to the opposite side QS. But BC is free, therefore QS must be also equal to 3 units in its length. In the next step, I call it the big triangle MPS in a new page, and we analyze this big triangle QMPS. Again, I'll copy the big triangle MPS in a new page, and we analyze this big triangle MPS. So actually, this is the big triangle MPS that I copied from the original drawing. MQ, line segment MQ, is defined as the median of this triangle MPS. And the definition of a median is the line segment that connects the vertex of the triangle with the midpoint of the opposite side. Here the vertex is M, the median MQ connects the vertex M to point Q, that is the midpoint of PS. Why point Q is the midpoint of PS? Because it bisects side PS into 2 halves. Each half equals to 3 units in its length. So the median of any triangle bisects the opposite side of the triangle. It exists from the vertex and bisects the opposite side of the triangle. The opposite side of the vertex M is PS. And therefore the median MQ bisects side PS into two halves. The question is, what is the length of the median MQ? We have a special formula for the length of the median MQ. So here we have triangle ABC. Side AB equals to B units in its length, side AC equals to C units in its length, and side BC equals to A units in its length. The red line segment AD is the median of this triangle ABC. It exists from the vertex A and it connects the vertex A to the midpoint of the opposite side of side BC. The opposite side of the vertex A is BC, and it connects the vertex A to point D, that is the midpoint of BC. That is to say, the median AD bisects side BC into two halves. Each half equals to BC over 2. So BD equals to DC equals to BC over 2. But what is the length of the median AD? The length of the median AD is equals to the square root of 2b squared plus 2c squared minus a squared over 2. So you can implement the formula in order to find out the length of the median MQ. According to the formula, the length of the median MQ is equals to the square root of 2 times MP squared plus 2 times MS squared minus PS squared divided by 2. Here we multiply this equation 1 by 2, and finally found out that according to equation 1, two times MQ equals to the square root of 2 times MP squared plus 2 times MS squared minus PS squared. Here we squared both sides of this equation 1. 2 times MQ squared is 4MQ squared, and here the square cancels the root, and we left only what is inside the root, that is 2MP squared plus 2MS squared minus PS squared. So in this side of equation 1, we have 4 times MQ squared. But according to equation 2MQ squared equals to R squared plus 49. Therefore, we substitute MQ squared here by R squared plus 49, and it is equals to 2 times MP squared. According to equation 1, MP squared equals to R squared plus 25. Therefore, we substitute MP squared here by R squared plus 25, and we have also here 2MS squared. According to equation 3, MS squared equals to R squared plus X squared. Therefore, we substitute MS squared here by R squared plus X squared, and we have also minus PS squared. PS in total equals to 3 plus 3, that is 6. Therefore, PS squared is 6 squared, that is 36. And therefore, minus PS squared is minus 36. We open the brackets on this side, on both sides of this equation 1, and find out that 4 times R squared, 4 times R squared equals to 4 times 49 is 196, so it is plus 196, and it is equal to 2 times R squared plus 2 times 25, that is 50, so it is plus 50, and we have also 2R squared plus 2X squared minus 36. Here we subtracted 4R squared from this equation 1, so 4R squared get cancelled. Here 2R squared plus 2R squared is 4R squared, so those two expressions also get cancelled. After we cancel 4R squared, in the side of equation 1 we have to leave 196. On the other side of this equation 1, we have 50 minus 36, that is 14, plus 2x squared. So in total, according to equation 1, we should find out that 196 equals to 14 plus 2x squared. Here we substitute 14 from this equation 1, and finally found out that 196 minus 14 is 182. So 182 equals to 2x squared. Here we divided this equation 1 by 2, and finally found out that 192 over 2 is 91, so 91 equals to x squared. Here we took out of this equation and finally found out that x equals to either the square root of 91, and the square root of 91 is 9.54. So what we found out that the length of this tangent MF is equals to x, it is equal to either the square root of 91 units. On terms of numbers, the length of this tangent MF is equals to x is equal to 9.54 units. So we finish the first question. And then I presented to the second question and solve the second question of this lecture. Our mission in the second question is to find out the length of tangent AEP is equal to x. We have to find out the value of x. So in the moment we have quarter circle AOB. Inside this quarter circle AOB we have this small circle. The small circle touches the big quarter circle internally at point K. And we have line segment OB, this is tangent to this small circle at point Q. Tangent AEP is tangent to this small circle at point P. Again, our mission is to find out the length of AP is equal to x. We have to find out the value of x. First of all, we define the center of this small circle. This point is point C, and we join point C and Q together by a straight line. CQ is of course the radius of this small circle. We define the radius of this small circle as A, therefore CQ equals to A. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join point C and P together by straight line. CP is of course the radius of this circle that is A, and according to rule 1, this angle equals to 90 degrees. In the next step, we join points A and C together by straight line. By joining points A and C, we can get the right triangle ACP. So in the next step, we'll cover the right triangle ACP in a new page, and we implemented the Pythagoras theorem on this right triangle ACP. This is the right triangle ACP, that is coming from the original domain according to the Pythagoras theorem. In this right triangle ACP, AC squared, that is the square of the hypotenuse, equals to AP squared plus PC squared. So AC squared equals to AP squared. AP is x, therefore AP squared is x squared, plus PC squared. PC is a, therefore PC squared is a squared. So the total according to equation 1, we actually found out that AC squared equals to x squared plus a squared. We have an internal notch between the small circle and the big quarter circle. That is to say they touch each other internally at point K. Whenever we have an internal notch between two circles, we can implement rule 9. According to rule 9, if two circles have an internal notch between them, then the straight line that connects the circles together must pass for their tangent point. The center of this quarter circle is 0 at point O. The straight line, the center of this small circle is 0 at point C, and the straight line that connects the circles together is of course the straight line OC. And according to rule 9, the straight line OC must pass for their tangent point, that is point K. Again, according to rule 9, the straight line OC must pass for point K, that is their tangent point. Or OCK is one straight line. Again, OCK is one straight line. So we join points O and C together by a straight line, and from the drawing it is very easy to see that indeed the straight line OC passes for point K, that is their tangent point. CK is the radius of this whole circle, that is A. OK is the radius of this big quarter circle, that is B. CK is A, OK is B. Therefore OC equals to OK minus CK. Again, OC equals to OK minus CK. So OC equals to OK, that is B, minus CK, that is A. So in total, OC equals to B minus A units in its length. In the next step, I copied the right triangle OCQ in a new page and implemented the Pythagoras theorem on this right triangle OCQ. This is the right triangle OCQ that I copied from the original domain. We just right now found out that OC equals to B minus A. CQ is the radius of the small circle, that is A. OQ equals to 5 units in its length, according to what is given in the question. So according to the Pythagoras theorem, this right triangle OCQ, OC squared, that is the square of the hypotenuse, equals to CQ squared plus OQ squared. OC is B minus A, therefore OC squared is B minus A squared, and it is equal to CQ square. CQ is there, therefore CQ square is A square plus OQ square. OQ is 5, therefore OQ square is 5 square. So in total, according to equation 2, we can find out that B minus A square equals to A square plus 25. B minus A square is B square plus A square minus 2 times AB, and it is equals to A square plus 25. We have A square on both sides of this equation, equation 2, so A square will get cancelled, after we cancel A square. In this side of this equation 2, we left only with B square minus 2AB, and the other side of the equation 2, this equation 2, we left only with 25. So in total, according to equation 2, we should find out that B square minus 2AB equals to 25. The next step, we did the construction, that is to say, from this point C, we draw perpendicular on AO. Again, from point C, we draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the transition point of the perpendicular from point C and AO. This point is point N. By doing this construction, we get quadrilateral NCQO. Inside this quadrilateral NCQO, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 facing angle must be equal to 90 degrees inside. So inside quadrilateral NCQO, we have 4 angles, and according to rule 5, any quadrilateral that has 4 angles must be this right angle plus a square. So we write to this quadrilateral NCQO as a right angle because it has 4 angles. But we also know that the opposite sides of right angle are equal to each other. So left angle NCQO, side OQ must be equal to the opposite side NC, but OQ is 5, therefore NC must be also equal to 5 units in its length. Likewise, according to the same rule, the same left angle NCQO, side CQ must be also equal, side CQ must be equal to the opposite side NO. But CQ is there, therefore the opposite side NO must be also equal to a unit in its length. What is the length of the missing line segment AN? AN equals to AO minus NO. Again, AN equals to AO minus NO. So AN equals to AO, that is B, minus ON, that is A. So in total, AN equals to B minus A units in its length. In the next step, I call it the right triangle ANC in the new page, and we've divided the also on this right triangle ANC. So okay, this is the right triangle ANC that I call it from the original domain, according to the Pythagoras domain. In this right triangle ANC, AC squared, that is the square of the hypotenuse, equals to AN square plus NC square. AC square, according to this equation 1, AC square equals to X square plus A square. Therefore, we substitute AC square here by X square plus A square, and it is equals to AN square. AN is B minus A, therefore AN square is B minus A square, plus NC square. NC is 5, therefore NC square is 5 square, that is 25. So in total, according to equation 3, we should find out that X square plus A square equals to B minus A square plus 25. So according to equation 3, X square plus A square equals to B minus A square. B minus A square equals to B square plus A square minus 2 times AB plus 25. We have here A square on both sides of this equation 3, so A square will get cancelled. After we cancel A square, in this side of this equation 3, we left only with X square. On the other side of this equation 3, we left with B square minus 2AB plus 25. But according to this equation 2, B square minus 2AB equals to 25. Therefore, we substitute B square minus 2AB by 25. So in total, X square equals to B square minus 2AB, is 25 plus 25. So X square in total equals to 25 plus 25, that is 50. X square equals to 50. Here we took out of this equation and we found out that X equals to the square root of 50. 50 is 2 times 25. Therefore, X in total equals to the square root of 25, that is 5 times square root of 2. In total, this expression equals to 5 times square root of 2. So in total, we should find out that the length of this line segment AP is equals to X. It is equal to either 5 times square root of 2 units in its length, but in terms of numbers, the length of this line segment AP is equal to X is equal to 7.071 units in its length. Okay, thank you very much.